In chemistry, frequently, it is necessary to measure the concentration of a solution. One technique for such measurements is the laboratory procedure known as titration. Titration is an analytical method in which a standard solution, one where the concentration is known, is used to determine the concentration of another solution. If an acid and base is added together, a neutralization reaction occurs. The acid unites with the base to form a salt and water. When conducting a titration, many different pieces of equipment are used. We have a burette, droppers, a pipette filler, a pipette, acid, base, spinner, beakers, a flask, a clamp stand, and of course our goggles to make sure we're protected during the reactions. So, how do we conduct a titration? Well, we're going to show you how. First, you want to make sure that all of your materials are cleaned thoroughly so that no contamination occurs. When doing a titration, errors, just very slight ones, can affect your results greatly. Then after you've washed them, you want to make sure that they are dry. In the titration we're going to do today, we're going to be using 1 molar hydrochloric acid and a base of unknown molarity. After labeling your materials, you're going to fill your beaker, one of your beakers, up with hydrochloric acid and then pour that acid into a funnel that leads into your burette. You're then going to take down how much acid is in your burette on your piece of paper so that when you're done with all your titrations, you have all your results right in front of you. Now you're going to fill up your pipette with exactly 10 milliliters of base. Make sure that the meniscus is right on the line so that you have exactly 10 milliliters of base and that your results are not skewed. Once you have the base, you put it into a flask. You then put the spinner in and finally put in phenolphthalein. By adding an indicator to the base, chemists can see at what point complete neutralization occurs and thus determine the concentration of one of the solutions. Eventually, after titrating a while, a color change of the indicator occurs with the addition of a single final drop, indicating the endpoint of the reaction. The endpoint is the perceptual event at which the indicator actually does change colors, and you decide the titration is over. The endpoint, however, can be far off. The equivalence point is much more accurate. The equivalence point means the moment at which the amount of acid added is chemically equivalent in terms of moles to the amount of base in the flask, so the two kinds of reagents are exactly canceling out. When doing a titration with hydrochloric acid and sodium hydroxide, phenolphthalein is a great indicator to use. After your titration is over, you want to make sure to note how much acid is left in the burette. You're going to put this on your paper as 24 cubic centimeters for this neutralization. That means 11 cubic centimeters are used for this rough titration. A rough titration just means we're trying to get a sense of how much acid is necessary to neutralize our unknown base. Now we're going to do a much more accurate titration, starting with a value of 18 3/5 cubic centimeters of acid in the burette. The technique for the next titration will be mostly the same as the first one, the rough one, but there are some major differences we will use. First, we'll add water to the base in the flask. When you add water to the flask, the concentration of the sodium hydroxide will change, but the number of moles will not be affected at all because you have not changed the number of grams or molar mass of the NaOH. Then, when you add HCl, you will know how many moles of HCl were added based on looking at the burette. In addition, the reaction occurs in the flask, which means both the HCl and NaOH will be equally exposed to the water. For this titration, like the last one, you turn on your spinner. You start the flow of acid into the flask from the burette, and then after a while you add some more water to the sides of the flask so that none of the HCl or NaOH gets wasted in the reaction and affects your results. Then when it's close to neutralization, you do drip by drip into the flask to make sure that your results are as accurate as possible. And after a while, when the phenolphthalein turns clear, you know neutralization has occurred. Then check the burette to see how much acid is left and make sure that you record your results so that you can come back to them later. 8 3/5 cc's were left, so that means 10 cc's were used during the reaction. Now we're going to fill our burette back up with acid so that we can do some more titrations to make sure that our results are consistent and accurate. After filling it up, we see that we have 36 and 1/2 cubic centimeters of acid in the burette. This will be our starting point for the next titration. We go through the procedure again, making sure the acid in the burette flows into the flask. And once we are done with the reaction, we have a clear solution, and we see our results: 26 and 1/2 cubic centimeters of acid left in the burette. Again, 10 cc's of acid were used. For our final titration, we start with 26 and 1/2 cc's of acid in the burette. After dripping some into the flask, we get 16 and 1/2 cc's of acid left in the burette after neutralization occurred. Now let's look at our results. We get rid of the rough titration result because that was less accurate. We see that our results were very consistent. We add them up: 10 plus 10 plus 10 equals 30 cc's divided by 3, and we get our average amount of acid as 10 cubic centimeters. Here are the results and knowns that we have. We can now use the equation: the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base, to find the unknown molarity of the base. We have the molarity of the acid equals 1 molar, the volume of the acid 10 cc's, the molarity of the base is still unknown, and the volume of the base that we used in the pipettes was 10 cc's. After writing down this information, it is very easy to solve for the molarity of the base. What we do is 1 times 10 equals 10 times molarity of base equals the molarity of the base times 10. We divide 10 times the molarity of the base by 10 and divide the 10 on the other side to find that 1 molar equals the molarity of the base. It was great doing the titrations with you, and we hope that you listen in to future podcasts. This has been brought to you by Stephen, Adrian, and Sion.